What is going on, guys? Welcome back. In today's video I want to show you one of the most interesting and one of the most useful Python modules that I've ever seen, especially for those of you guys who are in math heavy fields like computer science, mathematics, physics, and especially if you are still at university and you need to work with mathematics on an everyday basis or at least on a regular basis. This module can revolutionize the way you do your homework, your assignments, whatever, because this module can literally solve equations for you and do very complex stuff in mathematics for you. You can double check your solutions with it, you can solve the assignments with it, and one of the most important things for me is you can automate mathematical tasks, and I have not been able to do that without that library before, and I always wanted to do it, and this library is very revolutionary if you are in math heavy fields. So let us get right into it.
It's not a game, it's a rich thing.
Alright, so the library that we're talking about today is called SymPy, SymPy with a Y, not SymPy with an I. I also have a tutorial on SymPy with an I, which is about simulating real-life processes in Python, but SymPy with a Y is about symbolic mathematics. And in order to install this library, we're going to open up a command line, and we're going to type pip install SymPy, like this. And you can see, in my case, already installed. And once you have that, we're going to import SymPy, and I'm also going to import here, for demonstrational purposes, the core Python module math. And the reason I'm importing math here is because I want to show you the difference between calling a math function that has the same name and calling a SymPy function that has the same name. So if I print here, for example, math.sqrt16, and I also print SymPy sqrt16, in this particular case, because the number is 16, we're going to get the same result. So you can see we have 4 and 4, and yes, math returns a floating point number, and this one is an integer here, but it doesn't really matter. They have the same value. They return the same value. If we change now 16 to 15, or any other number that doesn't have a convenient square root, we're going to see the difference between those two libraries. You can see now that math still produces or still returns the exact value of the calculation, square root of 15, whereas SymPy stays symbolic and gives us the more convenient representation of square root 15. If we change this to 25, we're going to see again that the square root is going to be 5, because that's a convenient number to write. But if you have something complex that doesn't have an easy square root, like 26, you're going to get square root of 26, because this is more convenient for equations. So just because the functions have the same name, they don't have to have the same functionality. SymPy is more symbolic, math is about calculations. So having said that, let's start with the basics of SymPy. We're going to start by importing from SymPy the symbols, and symbols are essentially the foundation of the whole library. Symbols are what allow us to do equations, to do formulas, to differentiate, to integrate all that, because at the end of the day, in Python we have variables, but we cannot use those variables as equation symbols. They're just variables with values, and yes, we can calculate, we can do calculations with them, but we cannot use them to take the derivative of a function, for example. If we want to do that, we need to turn them into SymPy symbols, so we can say something like x equals symbols x, and y equals symbols y, for example, and then we can create a simple expression. We can say expression equals 2 times x plus y, and now this is treated as an actual equation. This is not or expression. This is not just a calculation. This is not going to have a value in the end, which is 2 times the value of x plus y. This is going to be treated as individual symbols of an expression. And you can see that this is the case because I can now say expression, and I can also say expression minus y. And then you can see that this will give me the full expression, and this here will remove y from the expression here. And I can also do the same thing with x, and you're going to see that in this case it removes the 2, because if I have 2 times x plus y and I remove an x, I only have 1x. So SymPy actually understands what is happening. So we can evaluate expressions, we can remove symbols, we can subtract symbols, we can multiply with symbols and all that. Which brings us to the next point, the way that these expressions are displayed. So if I have something like 2 times x plus y, the default representation of that is, if I type print expression, 2 times x plus 2 times y. So it evaluates that. It expands that formula. It takes 2 times x, 2 times y, which is correct, of course, but we don't have this representation. If we want to have that representation, we need to go ahead and we can import here factor, and we can import expand. And then I can just say here that I want to factor this expression. And you can see that now I have the factored expression. And of course, I can take another expression, expression 2, and I can say that this is 2 times x plus 2 times y. And then I can print that expression, expression 2. And actually, this is not what I wanted to do. Sorry, I wanted to do the opposite. I wanted to take an expression like this one. If for some reason you have an expression that you want to expand, so if you have it in that representation and it's also printed in that representation, you can just call the expand function instead of the factor function, and it will turn something like this into that. If you call factor on this, it will turn into that. So you can do that manually if you don't like the default automatic way that SymPy does things. So you can factor and expand manually, and this can be done for all sorts of things. We can, for example, say here that we want to have the expression x to the power of 2 plus x times y, and then you can see that this is the expression, and now I can go ahead and just say factor this expression. There you go. And I think that maybe an example for expand could be, let's try expression 3 is x times x plus y. I think this by default will not be expanded. I'm not sure about this. Let's see. Yeah, you can see that this now here is not expanded by default. So I can go ahead and say expand, and then you can see that this is going to turn into x squared plus x times y. All right, so these are the very basics of SymPy. Let us now move on to something more interesting, which is taking the derivative of functions, integrating functions, and working with limits. And for that, we need to import a couple of more things here. We need to say from SymPy import diff, import integrate, and import limit. And also we want to import OO. And I'm going to explain what OO is here in a second. Might be a little bit confusing for you right now. And let me just see here. I'm not blocking anything, but I'm gonna make my camera a bit smaller. So essentially what we can do here is we can say we have some formula, and this formula is, for example, x to the power of 2, and now we want to take the derivative of that. So we can just go ahead, and this is actually very, very useful. I can say diff formula. And then you can see that it takes the derivative of x squared, which is 2 times x. And I can do that for all sorts of formulas. I can say x to the power of 2 plus 5 times x plus 16 plus x to the power of 5 times 9 or something. And it will give me the correct derivative. At least I hope it's the correct derivative. So this is very powerful, and yeah, we can also do that with multiple variables. So if we have something like diff x to the power of 2 plus y to the power of 2, I can derive for x. I think it's called deriving for x. I'm not sure about how you say that, but you can see now it takes x squared and it makes it 2 times x, and it ignores y squared because that is just something that you add to the thing, right? There's no x in here. This could be just 5, right? It doesn't really matter. Y is not important here. Y is just one more value that is added to the equation, so we can just drop it when we derive. Same thing if we, for example, say y times x to the power of 2, then in this case we would get 2 times x times y, because that is just a factor. This is nothing that we derived. This is just a simple factor. This is the same as just saying 10 or 15 or 16 or any other number, just a factor. We can do the same thing for y. And then you can see we get a different result here. So x squared in this case is not derived because obviously this is just a factor. So we don't turn this into 2x. This is just one number, and it doesn't really matter what number that is. This is just a factor. Right, so we can do that. We can do the same thing here also with different functions like differentiate, SymPy, exp, x. and x is essentially e to the power of x, and we know that the derivative of e to the power of x is e to the power of x. So in this case, you can see it's still e to the power of x. And we can also do the same thing with cosine and sine. So we can say diff SymPy sine of x plus, I think I entered the wrong mode here. So SymPy cosine x, there you go. And you can see that this also takes the derivative of that. So this is very powerful if you have to do some homework, or if you have to do if you have to take the derivative of a function multiple times. If you want to automate that process, this is an invaluable tool, because even if you are super good at math and calculus and whatever, you want to automate this. And if you have 1,000 equations for some reason, or if you have to take the derivative of 1,000 equations, this can be automated using SymPy. Same goes here, obviously, for the integral. I can take a function or a formula, and I can integrate that formula. So I can say print integrate formula. I don't think that I have to specify anything to take the integral, and you can see now in this case x to the power of 3/3, which is the integral of this here. And you can play around with different formulas here. What do I have prepared here? I have 2 to the power of x plus 2 to the power of y, and I can specify here that I want to integrate for x. And then you can see this is the integral of that. And the interesting thing here is that we can also specify ranges. So I can say now that I want to integrate some formula, and I want to also specify the range. So basically saying the integral from one value to another value of this. So in this case, I would say from 0 to, or actually 4x from 0 to 10. So we want to integrate 2 to the power of x for x with the range 0 and 10. And this would then give me an actual value, obviously. So I'm not going to explain the basics of calculus here, by the way. So if you don't understand why this produces an exact value, and if you don't understand why certain derivatives are what they are, you should take a calculus course if you want to learn those things. Today I'm just showing you how to do that with SymPy. So what is this OO thing here? This OO thing here looks a little bit like infinity, and it actually is infinity. So sometimes you want to take the derivative, not the derivative, you want to integrate a function from 0 to infinity, or from negative infinity to infinity, to see what you get as a result. For example, what could we have here? We could say that we want to have the integral of the SymPy dot sine function of x, and we want to integrate that for x from negative infinity, so negative OO. OO is a placeholder for infinity up until OO. So this would give us then accumulated bounds negative to 2, so anything in between here. We can do the same thing with x squared, and I think then we should get a different value, right? Yeah, then we get the actual value, square root of 2 times square root of pi divided by 2. So you can play around with that. Again, you can just take your homework, you can just take your assignment, you can just take your task, whatever you're doing, and translate it into SymPy code. And I think it's quite intuitive, because you have the formula, you specify the variable, and you specify the range. If you don't want to specify the range, you can just only specify the formula and the variable that you're integrating for. One more thing that I want to show you here, I think I prepared these particular functions that I have here because they are interesting. I saw these examples online. For example, we can say 1 divided by x to the power of 4 plus 1. And we want to integrate that for x from 0 to infinity. And this gives us the square root of 2 times pi divided by 4. You can do the calculation if you want to see why that is the case. And the last thing I want to show you from this category here is also limits. And limits are very fascinating to me. Limits essentially in mathematics is, you have something like lim, and then you have below the lim n goes towards 0. What is the value of whatever is in here in lim? Or n goes towards infinity. What is the value of this particular thing, right? So we have these calculations. What could be such a thing? Let's start with a very trivial thing. If I want to know the limit, So what is the value of x if x goes towards 0? Well, obviously, if x goes towards 0, the value of x is going to be 0. Then we have something like, what's the value of x if x converges towards 5? Obviously, the value is 5. And then we can do that with different things. So what happens if I say x to the power of 2? If x converges to 5, this is obviously going to be 25. But this is not what you do usually with limit calculations. Those are pretty easy things that are just calculations at the end of the day. You can do something more interesting. For example, we all know that it's forbidden to divide by 0. But what happens if I say I have the formula, I don't know what, let's say 50 divided by x, and x goes towards 0. Now, going towards 0, converging to 0, doesn't mean that x is actually 0, because 50 divided by 0 doesn't exist, it's undefined, we cannot do it. But what if I would go endlessly, infinitely close towards 0? If x is basically 0, what would the result of 50 divided by x be? And of course, the answer here is infinity, so 0, because the smaller x is, the larger the value of the full thing here is. So we can always decrease x a little bit and a little bit more, and this goes towards infinity. This is the idea of a limit. And we can do some more interesting things here. So of course, if I say now x doesn't go towards 0, but x goes towards infinity, this is going to go towards 0, because the larger x gets, the closer this will be to 0, even though it will never be 0 actually, because no matter how big x is, how large x is, this will never be 0. It will always be a little bit more than 0, but if you are talking about limits, this will converge to 0. And then we have also, I think this one is kind of interesting, if we have SymPy dot sine x divided by x, and x goes towards 0. I think this produces a cool value. This is 1. And if we just have the sine and we go towards 0, this gives us 0, right? So this is kind of cool actually, and this is particularly cool because this here is 0, but this here produces 1, even though that is 0. If you think about it, just in terms of calculation, 0 divided by something cannot be 1. This here converges to 0, but this here does not. So very interesting to work with limits. And this is something you can do with SymPy as well. You can automate all of this if you have to do some tasks in that field. And yeah. Now we can also use SymPy in order to solve equations. And for that, I'm going to get rid of all this here. And also this here, and at the top here I'm going to import EQ for equation and solve for solving the equation. And then we can have the equation, for example, x times 2 or 2 times x plus 5 is equal to 0. And if I want to solve that equation using SymPy, what I do is I say print solve and then just 2 times x plus 5, and I don't have to specify the 0. Because whenever I have an equation of the format something equals 0, I just have to paste here, or I just have to pass the something here into the solve function, because it automatically is going to assume that the right side is 0. So in this case, we're going to get -5 divided by 3. We can double check this. So if I enter here -5 divided by 3, -5 divided by 3, and if I evaluate that in Python and just print the result, this should be 0, and in fact it is. So I can get rid of this now. If we want to have the structure something equals something else, then we need to use the EQ keyword, because then we have to also specify the right side. So what we do here is we say EQ, and we specify, for example, x to the power of 2 is equal to 16, and I want to know what x is. In this case, x can be 4 and -4, obviously. Because 4 and -4 squared are 16. We can do the same thing, by the way, also with variables or with symbols. So I can say x to the power of 2 is y, but then I have to specify, of course, what I'm solving for. And in this case, I want to solve for x. So inside of the solve function, the second parameter is x. I have this equation. I want to solve it for x. And then I get that the result for x is whatever y is, the square root of that, or the negative square root of that. And we can do all sorts of complex equations. We can do, we can also get imaginary numbers, so complex numbers. If I have, for example, x to the power of 3 is 16, for example, Then you can see that I get one normal solution here and then two complex solutions with the I, with the imaginary part. So that works as well. And of course, we have certain equations that are just impossible to solve. For example, if I have an equation where I say x minus 1 is the same as x, there is no number that fulfills this rule. There is no number that you can decrease by 1 and you end up with the same number. Because of that, we're going to see that we get an empty list as the solution here. And of course, we can get a lot of solutions if I say x to the power of 17 is 15. I'm not sure if this is going to take some time to solve. No, it actually works quite well. And you can see I have a lot of solutions here and a lot of imaginary or complex solutions here as well. But yeah, you can play around with that. You use EQ to craft some fancy formula, some fancy equation. You can also include symbols here. And of course, in this case, I didn't specify what to solve for, but I can solve for x again. And then I get some solutions. I can solve for y, and I get different solutions, and so on. Oh, actually, for y, I get quite simple solutions, obviously, because the power of to the power of 17 is on the side of x. So in order to get y, I just divide by 15, and I have the result. For x, it's a little bit more complicated. All right, so let us get to the last part here, which is more complicated, so I'm just going to briefly mention it. It's about differential equations and eigenvalues of matrices. You don't need to understand these concepts if you don't care about them, but if you know what they are, you can easily also calculate those. I'm just going to show you here quickly one example that I got from the documentation. The example says that we have a variable t, so a symbol t, and we have a symbol y. And the equation that we're solving is, I'm going to add this as a comment here, y of t derived 2 times, or differentiated 2 times, minus y of t is equal to e to the power of t. That is the idea, or what was it? Yeah, e to the power of t, and we want to differentiate, we want to solve this differential equation for y of t. Now, it's been some time since I worked with differential equations, but I hope I can at least type this in correctly. So the function that we need for that, and I'm gonna remove those two so that we see what we are importing here, is the dsolve function. So solving differential equations, we're gonna import dsolve, and we're gonna print here dsolve equation, and the equation is y of t, so we can also do that when we have the symbols. The symbols can also be functions. And we're going to say dot diff tt. This basically means take 2 times the derivative with respect to t. So we differentiate that function 2 times. We subtract then from it y of t. And then we have a comma for the right side. And the right side is SymPy x, so e to the power of t. And then we get out of this here and we want to solve for y of t. That is that. Let's see. Okay, we have a problem. Symbols not callable. Oh, sorry, I made a mistake. We don't want to call this symbol, obviously. I talked nonsense here. We cannot use a symbol like that. We need to call this function. And of course, we need to import function also from SymPy. So we need to, actually, we don't need all of this here. So I'm going to just say function. Because, of course, if we want to use y in that context with y of t, we need to specify this here as a function, whereas t is a symbol. So this is what you need to do here, and then you get that here as a result. Again, I'm not going to talk about differential equations, what they are, how they work, and how to solve them, but you can automate the process in SymPy here. And last but not least, I want to show you something about matrices. So I already mentioned that I want to show you here the eigenvalues, so we can just import matrix here. And if we have a simple matrix, I'm going to create a matrix with 1, 2, and 2, 2. Then we can take that matrix here and just compute the eigenvals. What's the problem here? Unresolved. Oh, I didn't import it. Okay. Why is that? I'm not sure. But then you can see that we get the result here as well. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and